Hello everyone, hope you're having a great day. Today we're going to begin a very compressed course in plasma physics. I'm standing up this course kind of in over a very short term to help provide my graduate students with a little bit more of the background that they need to tackle their research problems. And since I was planning on doing that, I decided to make a little course out of it and open it up to students across different departments who might be interested in plasmas. The course has a very permissible set of prerequisites. So as long as you have taken a course in differential equations and a course in made your way through a classical physics sequence, from just your standard year-long classical physics with calculus, then you should be able to hop in. Although I will say that the general level of the material is definitely going to be, fourth year undergrad, first year grad student level. Should be very comfortable for the fourth year physics major. Not too much of a stretch, a little bit more of a stretch for the fourth year engineering major, and then should be pretty manageable for first year grad students from either of those disciplines. Third year students can make their way through this course. There's just going to be a few topics that will be particularly challenging and will blow your hair back a little bit, but you should be able to make it through. I'm going to do my best to bridge from those kind of, let's say, lower division subject matter preparation from your physics sequence and from your differential equations course to this more high level topic. Okay, and like I said, the course is very compressed, so we're going to cover a lot of ground in just 10 lectures, and I'm hopeful that it'll give you a good exposure to plasma physics, but I don't want it to just be a quick survey either. We're going to get into the nitty-gritty details of a lot of these topics that you wouldn't necessarily see unless you were taking a full-on plasma course. So it's going to be a little spiky, not super broad, but we are going to cover a large breadth, but dive in across these various disparate topics, and hopefully cover some of the most important fundamental stuff. Hopefully with some level of detail, where we're able to be rigorous instead of just making this like a survey course. So because of that, because we're going to have people taking this class from all sorts of different backgrounds, we need to start by doing a bit of a review of E&M, or electrodynamics. I think that there's no better way of doing that than to start with, or make our goal for the day, let's say, to understand this set of equations. So the divergence of this vector quantity D, that's equal to F. That equation is called Gauss's law. Divergence of B equal to 0. That equation doesn't really have a name. And then the curl of the electric field E is equal to equal to the -1 times the time derivative of the B field. Okay, we call that Faraday's law. And then the last equation here is this curl of H equals JF, or your free current density plus the time derivative of the displacement field. Okay, there are four vector expressions. There's actually 8 equations in here, because the two equations on the right are vector equations. The two on the left are scalars. so they're only one equation. But like this thing is called the displacement field. You know, that little F subscript is telling you that you're talking about the free charge density. You know, this H we often call the auxiliary field. Auxiliary field. Okay, and then the B and E, of course, are your magnetic and electric field that you hopefully are at least a little familiar with. So hopefully by the end of today, you have a decent idea of what these equations represent, where they come from. And in order to do that, if you're starting from a place like just having taken a course in ordinary differential equations, you need to actually be able to understand what these vector calculus operators are doing, what this upside down triangle is, which might be called the del operator or nabla or the gradient operator. Okay, so we're going to start there actually. We're going to do a whole section here on just vector calculus operators. Okay, so hopefully this will be a review, but you know, this course is being taught in the mechanical engineering department, and even senior level mechanical engineers will not take in a vector calculus course. So and we're going to try to bridge that gap here, and hopefully I'll be able to take you along for the ride. If you've taken any fluid mechanics courses, especially upper division fluid mechanics courses, you should be familiar with the gradient operator, or the del operator, sometimes it's called. It's denoted as this upside down triangle, sometimes with a vector sign on top, sometimes not. I'll usually omit it because there's not really a reason to be disambiguate with that, because we always know it's this vector quantity. And it is the following, where you have, it's an operator, and it behaves like a vector with the derivative along the unit vector direction for each of the elements of the vector. Okay, so this thing can act on the scalar. So this operator can act on a scalar, and this is probably the context in which you're most familiar with seeing it, like with the gradient of the pressure, for example, would look like dp dx in the x direction plus dp dy in the y direction plus dp dz in the z hat direction. Okay. Broadly speaking, the entire gradient vector itself points in the direction of steepest change of p in R3. So points in the direction of steepest change in the pressure, say, in this case, in R3, okay? So this is another thing that I often ask students, like, where is the gradient pointing, and what space does the gradient live in, right? It lives in R3. It lives in this XYZ real space. So like, if you're in a corner of the room that has low pressure and there's a heater or something, or a source of air in the other corner of the room that has high pressure, and so you have airflow going this way, and you're standing in that in the middle of that room, the vector is literally an arrow that points towards the higher pressure corner of the room. Okay, it's like it lives in physical space. It's pointing in physical space. Okay, and so when I say act on a scalar, one thing I want you to be thinking about with all of these vector operators is that this thing is actually taking a scalar and it's operating on it and turning it into a vector, or the result is a vector. So you can think of this is a scalar to vector operator. One of the things that this operator is doing is it's actually changing the character of the thing that it's acting on. It can also act on vectors via the dot product. It can also act on vectors via the dot product, and you treat it just like any other dot product, okay? So this thing is called the divergence. And so like, let's say we have del dot u. Okay, so like with any other dot product, you multiply the components that have unit vectors that match, and then you sum them together. It's based on this concept of orthogonality, right? And so what we're going to end up with here is dux dx, so the x component of u, plus duy dy, plus duz dz. Okay, and then, as another note, here we're taking a vector and turning it into a scalar, right? And so now you can see why on the top of the screen here, the two equations that you see on the left, those are scalar equations because you're taking the divergence of a vector field, D and B respectively, and getting a scalar out. So each of those equations just represents has just a single coordinate wrapped up in it. Okay, so like I said, this operator, this del dot, is called the divergence. The divergence. And it is aptly named. So, and I'll explain why that is. It is aptly named. So, when a vector field has positive divergence, it's because the vectors, the field, are kind of spreading out. Okay, so like if you have, let's say we look at the vector field V, that is x hat plus y hat plus z hat, right? Well, what does that look like? If let's say that this is the origin, this is the, x, y, z equals 0 point, then close to the origin, it's always going to be these like radially pointing out little arrows that are small. But then as you get further away from the origin, the arrows start to point further away. They get larger because the magnitude of the vector is growing as you go further away from the origin. X, y, z, and so on are getting larger. And then, of course, as you continue to go, these arrows just get even larger. And I won't draw all of them here, but just so you can see what's going on there. So this vector field has positive divergence. And you can literally calculate that by taking the partial derivative of the x component with respect to x. You're going to get 1. So this vector field has a divergence of 3. Just 3 straight up. Okay? So this vector field has positive divergence. Okay, this vector field right here that I'll just draw, which we'll say it's v equals just z hat. Okay, so it's just a constant vector field everywhere that points in the z direction. That's just going to look like this, where it's just uniform everywhere. Okay, this vector field has 0 divergence. And then there's also this other type of case where the vectors are not necessarily spreading out from a location, but they're changing in magnitude as you move in one direction. So this is like, instead of v equals z hat, it's v equals z times z hat. So the further up you go in the z direction, your vector gets bigger and bigger. This one does actually have positive divergence. Okay, so the vectors aren't really spreading out, but there's some sort of like source that's causing the magnitude of the vectors to increase as you move through space. One way that you can kind of check at a glance, if you have a picture of a vector field, say, if a vector has positive divergence or not, is like, imagine you drew like a little kind of control surface somewhere in this vector field. And if you have more vector coming out, like a larger magnitude of vectors coming out than going in, like if you have if everything is equal in to out, then you know that you have 0 divergence. But if you have some sort of more flux in than out, or vice versa, through that little surface you drew, shrinking it down to an infinitesimal element, then you know you have something like positive divergence, and that's connected to Gauss's law, which we'll we'll discuss later. But for all of these vector fields, you can do that sort of check, and you would see that for the zero divergence case, that little control surface would have zero net flux, and then in the other two cases, it would have some sort of positive net flux. Okay? So no matter where you draw that control surface, in fact, in space. Okay? So that's divergence. Hopefully that made sense if you'd never seen that concept before. You can also, with this, and now going back to the type of operations we can perform with del, or the gradient operator, you can also act on a vector via the cross product. Okay, so that looks like del cross u. Okay, which in vector notation, you might write this way. Sometimes you do these triangle brackets to denote vectors, right? You have del x, del by del, d by dx, d by dy, and d by dz. That's your del operator. And you take the cross product of that with ux, uy, and uz. Okay. And then one thing that I like to do when I write out a dot product is I actually like to just draw a coordinate axis, so I don't have to memorize the dot product rule. And so then I know that this is x, this is y, this is z, and you can use the right hand rule. So if with your right hand you have your fingers straight, that's the first vector. So if my fingers straight are pointing in the direction of u, and then I move my fingers to the second vector, so if they're pointing in the direction of x, and then I dot them with y, then I know that I'm pointing my thumb in the positive z direction. Okay? So that means that the d by dx, the first component, okay, that's the x hat vector. When it hits the uy component, it's going to result in a positive du duy dx in the z direction. Okay, so hope that might be more confusing than it's worth. Some people like to just memorize this formula, but I think it's more worthwhile to just think about how the dot products work out. So you're going to have three components to this vector in the end, right? And so then, like I said, the z component is going to come from the x cross y component and the y cross x component. The x cross y component is in the positive z direction, so you know that that's going to be your d by d x cross y is going to be your d by d x of uy, so d by duy dx, and then the negative component is the z component, or sorry, the y component cross the x component, right? That's going to give you a positive or a negative z direction for the way your thumb is pointing in the right hand rule. So then you have dux dy. Okay, hopefully that makes sense. This is kind of harder to do through like a screen. In person, I could draw it on the board and orient my hand to sort of show you exactly what's going on there. But anyways, okay, so then the x component ones are going to come from cross products between the y and z components. So the y cross z component is the positive direction, so that means I'm going to have d uz dy there minus duy dz. Okay, and then the y components are going to come from the x and z cross products. I know that the z cross x is going to be in the positive y, so then I need du x dz minus duz dx. Okay, so that's what the cross product applied to u looks like. Okay, so what is what is this operator? So this is called the curl. Okay, so this is called the gradient cross is called the curl. And let me also highlight divergence up here. is called the curl, okay? And it's another one that's pretty aptly named. So let's look at the vector field, for instance, minus y x hat plus x y hat. Okay, what does this look like? Well, if I draw another coordinate plane here, we're going to have, if I just draw the vectors in the x and y plane, it's going to be this sort of little swirling field that looks like this. Okay, and then as you go further out, the vectors get a little bit bigger, just by the way that, virtue of the way that this this vector field is defined. Okay, and so in this case, if you look at the formula above, the curl of v that we just defined is just equal to 2 times z. So it points along the z-axis. This is the z-axis. You have x and y. Okay. Now, one way to think about the curl is that if you place a paddle wheel at a point, at a point in a flow meaning that what's being represented by this vector field. Okay, so the vector field is telling you where the material in a fluid flow is moving, for example, and that paddle wheel rotates. Then you place it at a point of non-zero curl. Then you placed it at a point with non-zero curl. Okay? So in other words, like the vectors on one side of the paddle wheel are pushing it in this direction hard enough where either in this direction it's not being pushed as hard, or it's pushing the other direction, and generally this thing is net net is rotating like this. Okay. I literally can't draw a paddle wheel, but it's like this. If this pencil had little like fins on it, and it was being turned, like if you placed it in the middle of a whirlpool, it would twist. Okay, so that's what we mean by curl. Okay, so those are kind of like the three most important ways that del acts on different types of scalar and vector quantities. But there's also product rules, right? So we all know the product rule for just scalar derivatives. But they're a bit different for vector operators. Now, again, so the formulas that I'm about to write down are things that you need to know exist. So like anytime you see the gradient or del operator applied to two things multiplied together, you need to remember that there's some special treatment that needs to be used there. But you generally don't have to memorize them. These are something that you would always, or in most cases, you would just look up. Okay, once you use them enough, you'll start to memorize them. I'm sure a lot of the physics students taking this course will just have it memorized, have these things memorized. But that's not necessary. So f is a scalar, a is a vector here. So we're taking the divergence of a scalar multiplied by a vector, both of which might be dependent on space. If you do that, then you get this result, f times the divergence of a, plus a, the dot product of a, with the gradient of f. Okay, so that kind of looks like a normal product rule, right? There's also a similar form product rule for the curl of f times a, which just looks like f times the curl of a, minus a, the cross product of a, with delta f, or sorry, grad f. Okay, now it can get more complicated. So like you can have like this rule where you take the divergence of a cross b, where a and b both are spatially dependent. Okay, in that case, you get b dotted with the curl of a minus a dotted with the curl of b. Okay, and many others. There's several other gradient operator product rules. So, another important thing to know, and this is particularly important because it's how we'll like derive the electromagnetic wave equation down the line, for example. There are also formulae for second derivatives. So like the curl of a vector field, or the gradient, or sorry, the divergence of the curl of a vector field, which as a note, this actually happens to always be 0. I would encourage you to go and actually just prove that to yourself using the definitions that we've covered. So there are also formula for these second derivatives. And again, I would say, in most cases, just go ahead and look them up. So just look them up. And if you wanted to derive them, you can actually construct them, or construct all of this, like all of these kind of product rules, by treating del, or the gradient operator, as a vector. Okay, so if you do all these vector products properly, treating del as a vector, then that you can kind of recover all of these things. All right, now there's some very important integral theorems or rules. So important integral theorems. So this is another thing where I think that undergraduate engineers do not cover these things, which is just astonishing to me. But we're going to do 3 minutes on it right now, just to get them out of the way. They actually don't say anything much more deep than, like, extremely deep once you understand what they're saying. But the first one is a theorem that actually has 3 names. So if it has 3 names, it's important, right? Sometimes it's called Gauss's theorem, or the Gauss theorem. There's another thing another name for it called Green's theorem, or the Green theorem. And then there's also people just call it the divergence theorem, just to kind of, I guess they were fed up with it being sometimes called Green or Gauss. Okay, so this theorem has the following statement. So, when I put this little v under an integral, it means I'm doing a triple or a volume integral. Okay, it says that the divergence of the integral of the divergence of a vector field over a certain control volume. Okay, so that dv with a little hash on it is me saying that would be like dx, dy, dz in Cartesian coordinates. Okay, so it's a triple integral that's being represented here. That is equal to the closed surface integral. Okay, and that surface integral is the boundary of whatever volume you are integrating over, of v dot dA, and dA is the outward facing normal times an infinitesimal area element. Okay, so this statement is really just boils down to this. It's saying that the integral of the sources / sinks in the control volume, so you're going over all of the volume and trying to see whether there's looking at the divergence of V. Like I said, it's seeing if the V is like spreading out or if any new V is being produced. So you're going through all of the inner volume and trying to look for production of whatever you're tracking, whether it's fluid flow or whatever. Okay. So you're looking at the integral over the sources and sinks in the CV by looking at the divergence, and then you want that to be equal to, of course, the flow in and out of the control surface. Right, so like if you're making mass, if mass is entering your system somewhere in your control volume, then it has to go somewhere, or like energy, for example. So again, just to reiterate, that control surface is the boundary of the control volume. Okay, so that's the first important integral theorem. It's not very mystical. It really is just like you're adding up all the sources and then setting that equal to the amount that goes in and out. It's just like a conservation statement more than anything. Okay, and then we have Stokes' theorem, or Stokes' theorem, depending on how you want to pronounce that. And this one says that the integral over a surface, okay, not a closed surface, just a surface, of the curl of V dot dA. Okay, so those are the surface elements. So remember, it's like if you drew a surface, it would just be like a bunch of vectors that are normal to the surface with some infinitesimal area. That is equal to the closed integral over the perimeter of that surface P of V dot dL. Okay, so like, just to be clear, that's the integral over the perimeter. So you're following, your path of your integral is following the perimeter of your integration surface S on the left-hand side. Okay, so this one's a little bit more mystical than Gauss's theorem. So the very common like figure that you're going to see that I think does a decent job of explaining it. So let's say that this is our surface S. Okay, and then I'll try to draw something like a recreation of it right here. Okay, so what are you doing when you with the left integral? Okay, you're going to every infinitesimal volume element and you're asking yourself, what is the curl there? You're essentially trying to see what the magnitude of the vector field's swirl, local swirl, is at every single point. And that's what I'm drawing here, is these little arrows that are circling in on themselves. Okay, and you're adding up how much that swirl is happening at every point. And so you can think about, one thing you can conceptually think about here, this end up looking like a bunch of little G's, but it's just little vectors that are curling in on themselves. Okay, all of the contributions of those curls on the interior are going to cancel, right? Because neighboring swirls have different directions. So like what I'm drawing right here, you'd have this arrow and the red arrow and the blue arrow are anti-aligned in the interior. So everything on the interior of the surface kind of cancels out. And when you add up all these curls, what you end up with is just the outer edge. And so you can add up all that same amount of curl, say, which is just measuring how much the vector field is turning around, by going along the edge of the parameter and just asking how much of the vector field is pointing along the edge. Okay, and sum all of that up, because everything on the interior is canceling out. All right, that's the way it was explained to me when I first learned Stokes' theorem, and I think that that's a pretty decent explanation if you don't understand it. So if you sum up all these, then you get that in effect. Okay, and so I don't know if the very first time that was explained to me, it totally made sense. But in retrospect, it's a good explanation. So once you do, I don't know if I'll be the one to get you to understand this, but once you do understand it, then this explanation will make sense. Now that was very quick coverage of divergence in Stokes' theorem. These are things that would make up a big chunk of the course load of your Math 255 class. You'd be doing a lot of work with these and plugging in these theorems to solve problems. So what I'm going to ask, because I know that they're the best visual learning tools online for this thing, I actually haven't found, I don't know what the exact video's name is. I'm going to put the best video that I can find for these topics in the description of this video that you can click on and go watch. But please go watch 3 Blue 1 Brown or Grant Sanderson's videos on these vector calc topics, okay? So like anything from the gradient operator to the divergence theorem and Stokes theorem, all these curl and divergence, all those things, I am almost certain that Grant has some amazing visual material for you to learn about these things. And I generally, recommend his videos without reservation because I think that they're the best visual math teaching videos ever made. I think he's like a gift to humanity, Grant Sanderson. So make sure to go watch those, especially if this isn't so much review, but rather you're seeing this for the first time and you're not really sure what I'm talking about. That would be a great place to go. Okay, but now that's kind of gets the basic vector calculus, vector operator stuff out of the way, and now it's time to start talking about some physics. Okay, and so we are going to, and hopefully you know Coulomb's law. This is something that you would learn hopefully as far back as high school, but definitely in your classical physics sequence. We're going to start at Coulomb's law, and we're going to make our way to Gauss's law, which was that first of Maxwell's equations that I wrote down at the top of this lecture. Okay, and it's basically, in effect, an abridged run through electrostatics, which is to say, just charges that are kind of existing in space and just hanging there. Okay, so we have Coulomb's law. This is something that was observed empirically. So we're kind of going along the historical route of developing Maxwell's equations here. And so we have this Coulomb force, Fc. It's equal to 1 divided by 4 pi epsilon naught. Epsilon naught is the vacuum permittivity. The exact value kind of escapes me at the moment, but it's something you can look up. If in chemistry class or in your high school or whatever, you might have seen this represented, this 1 over 4 pi epsilon represented as k, so like kqqq over r squared. I prefer to write it in terms of epsilon naught. So then you have a lowercase q and an uppercase q, so kqqq over r squared, and it points radially outwards, okay, from the point charge lowercase q. So lowercase q is a point charge at the origin, okay. Uppercase q is a test charge, okay, and then Fc is the force felt by the test charge as a result of the presence of the point charge lowercase q. Okay, and then there's one more thing. We need to define what R is. Okay, so R, and actually this is where I said, when I put point charge at the origin, that would make R just a general vector, but I'm actually going to get rid of that because it's important that we let Q, lowercase q and uppercase q, the test charge and the point charge, be located anywhere in space. And if we relax that sort of origin location assumption, then we can define R as the following, which is just R minus R prime, lowercase r's. Okay, so then R is the location of the test charge, so location of Q, the capital Q test charge, and then R prime is the location of the point charge Q. So it's the location of the source for whatever electric field is causing your force, your Coulomb force. Okay, so R and R prime start at the origin, wherever you place your origin. They point to the locations. The tip of the vector hits the location of the test charge and the point charge. Okay, so I can even just draw that really quickly on a coordinate axis. So let's say we had our little plus Q here, and we have a plus big Q there. Then R is going to start at the origin here, and it's going to point to Q, so that's R. And then R prime points this way, R prime. And then R, capital R, is like this, R. Okay? And then as a result, the Coulomb force is like this, FC. Okay? So it points along the R direction and it acts on the test charge, capital Q. Okay, so hopefully with that diagram that makes sense what we're talking about with all these different R's. All right, I remember when I first entered the paradigm sequence, which is the third year physics sequence here at Oregon State, all these R's and R primes really kind of overwhelmed and confused me. So please don't hesitate to come ask questions about what's going on there as we get into the course, because especially for this lecture, we're going to see a lot of integrals over R prime with R's present, and it's going to your head's going to spin if you're not familiar with it, and that's okay. I'll help you get there. All right. So that's the Coulomb force. Now, let's talk about what the definition of the E field is. Okay. So the force felt by a test charge, capital Q, in an electric field or E field, that is E, is Fe, it's equal to the test charge magnitude times E. Okay, that's just like the definition. So then that means that if we wanted to write what the resultant E field is from a point charge, then we get 1 over 4 pi epsilon naught times Q, the point charge value, the source, over R squared times R hat. Okay, if we had a group of n point charges, then the total E field that results from all of those would just be a superposition of all the fields. So you just add up all the fields that result. So you have 1 over 4 pi epsilon naught times the sum from I equals 1 to n of Q sub I, so the charge of the ith point charge, divided by Ri squared times Ri hat. Okay, hat just means normalized vector here, if I didn't say that before. So you sum up all those different directions, and then that would give you a total vector field, or a vector quantity that would be your total E field that results from all of those things. And then, so that's just summing up a bunch of point charges, but then you can also, take this to a continuous distribution. So now say you have a continuous charge density distribution rho of R. R prime, it would be rho of R prime, right? Because this is the source material. So I'll put a little C for charge density. Just actually, I think I'm going to drop it because in E&M that's often not put there. So let's just assume that whenever you see a rho, unless otherwise stated, you're talking about a charge density. Okay? So if you have that, then it becomes an integral. Just like because an integral is just a sum, right? But it's a sum over infinitesimal volume elements. So here we're going to have E tot is 1 over 4 pi epsilon naught, but now we're going to integrate over all space, negative infinity to infinity. And this is a stealth triple integral again. And we're going to integrate over rho of R prime. Okay? Now I'm going to bring out, I'm not going to write capital R anymore. Now it's time for the gory detail. Okay? We're going to have R minus R prime, not normalized. Okay? So I'm basically bringing the magnitude back into the numerator. And for that reason, on the denominator, I have to put the magnitude of R minus R prime cubed. Okay? So before I had the squared on the bottom and then a normalized vector on top, the R hat. Now I have a non-normalized vector on top, so I need to pick up an extra magnitude on the bottom. And then we're integrating over dV prime, so the location of the source charge material, that distribution of charge. And just to be clear, that dV prime is actually dx prime, dy prime, dz prime. It's a stealth volume integral. Okay, I'll even put a little v under the integral sign just so that's clear. Okay, so you've gone from single point charge to the field produced by to the field produced by a continuous distribution of charge, some sort of volume charge density, let's say. And that's how you can get the total field. And also I should just to kind of help you see this resultant field is a function of R. Okay, if you look at the integral, there's still those unprimed R's in there, and that's your position of where you want to put your test charge or where you want to evaluate the E field. Okay, that's your free so you can say that the E field, that's a result of this material at the primed location. Here's how it varies in space as a function of R. Okay. Okay, like I said, this R and R hat thing, I'm sure it's going to confuse a lot of students that are not in the physics department. But just come chat with me and I'll draw some pictures and we will definitely get there. It's just one of those things you need to see and get some practice with. I promise you'll eventually understand it. But it is important to use that notation for when we're talking about E&M. Okay, so then we're going to, instead of a volume charge density distribution, we're actually going to take a step back. So take a step back to a simple to a point charge. Take a step back to a point charge. And then we're going to surround it by a fictitious control surface. Surround by, and in fact we'll even use a spherical control surface. Okay, and we're going to put the with the point charge at its center. Okay, so why are we doing this? What we want to do is we want to calculate the flux out of the source. Okay, so want to calculate flux out of the source. So what is flux? Flux is the amount of, it's the strength of the vector field multiplied by the area that it's going through. So if you're talking about flow rates of fluid, the volume flow rate is the flux of a vector field that is representing fluid flow, for example. Okay, if you're familiar with fluid mechanics, for E&M, we're just looking at like it's a way of looking at the density of electric field vectors going through a certain surface, and it's also, you know, if you have a closed flux surface and you get some sort of positive flux out, you know there must be some net charge contained inside, right? And so what we're trying to do is we're trying to get trying to find a relationship between the charge contained inside this flux surface and the E field expression that we found before. So what are we looking at? This is the image that I'm discussing here looks like this. We have a plus Q at the center. Let me make that that axis a little bit taller, and we have just this spherical surface that's enclosing Q. Okay, and of course it has E field, you know, kind of coming out of in all directions from the Q because it just points radially outwards, and we know this. Okay, and so let's do it. Let's say we want. So what does that integral look like? Well, it's a closed surface integral over our surface, and you just take the dot product of E with the differential volume elements that make up the surface. Okay, with the outward normal, and then we can just plug in our expression for the E field into that. So we have the 1 over 4 pi epsilon naught, and then we're going to have. I'm actually going to go back to using the capital R here because we're going to work in spherical coordinates, which makes it a little bit simpler. So we can use R squared times R hat. Okay, that's our expression for the E field resulting from that point charge Q. And then when you do this volume integral over 3 dimensions, what you pick up is this R squared sine theta d theta d phi d theta d phi rather. Times R hat. Okay, so that's what the outward facing normal surface element on the surface of the sphere looks like. It's R squared sine theta d phi. Hopefully you guys remember this from your multivariate calculus doing volume integrals in different coordinate systems. So it's just spherical coordinates. And you can see that there's this really convenient thing that happened here. The R squareds cancel because of the spherical symmetry of this force. And so now suddenly we just have a total constant, okay, because the R hat dot R hat is just 1. We have Q over 4 pi epsilon naught times the surface integral differential element. And if we integrate that over, 2 pi in theta, and pi over pi and phi, or vice versa, whichever one you want to call which. I think in this case, theta is the azimuthal direction. Then what happens is you the 4 pi, you just get a 4 pi out and it cancels, and you get just Q over epsilon naught. Okay? So that's really nice. Just the total flux out of the source is just equal to the charge enclosed, the point charge enclosed divided by epsilon naught. That seems like a pretty simple relationship, and we're getting very close to that first of Maxwell's equations now. So if we replaced this test charge with a collection of charges, you could just make the surface bigger, and you could then just sum up all the different integrals, right? You could just keep summing up integrals. And so if we define the Q enclosed as the sum over I of all the test charge values, the point charge values, then you'd arrive at, the integral of E dot dA is equal to Q enclosed divided by epsilon naught. Okay, and in the continuous limit, so like not just a bunch of discrete point charges, but a charge distribution, you can write Q enclosed as an integral over volume, over the volume of your surface, of rho dV. Okay, so that's just making the jump from a single charge to a distribution charge. We're going to go back and forth here, back and forth. And now we can invoke the divergence theorem, because so we have that E dot dA over a closed surface, right? So we can rewrite the closed surface integral of E dot dA as the volume integral of the divergence of E dV. And we just found out that that's equal to 1 over epsilon naught times the volume integral of rho dV. That's their Q enclosed value. Okay, and this holds for any volume. Because our volume was fictitious, we can sort of reform it however we like. And so that means that we can drop the integrals and just write that the divergence of E is equal to rho over epsilon naught. Okay? And that's your sort of Maxwell equation number 1, or Gauss's law. Gauss's law is what we call that one. All right, so we just kind of went through that development of, we started with Coulomb's law, and then we showed how we can arrive at Gauss's law mathematically here. All right, so let's push on. All right, we need to start bringing magnetic fields into the mix, right? So the first way we're going to do that is with the Lorentz force, and this is a very important relation, because this is the force ultimately that tells the particles in plasma how to move, okay, because they're charged particles. So the question, like I said, is we need to ask is how do magnetic fields interact with test charges? Right, so we know what's happening with a static electric field, but what about magnetic fields? Okay, and the answer to that question, of course, is the Lorentz force. So the force that the test charge feels is Q times, remember Q is the magnitude of the test charge, times E, so that's that electric field that we already know, that we've already discussed, plus V cross B. V is the velocity of the test charge. Okay. So let's draw what I mean here. So let's say that we have this coordinate set of coordinate axes. All right, and we got the test charge Q, and that charge is moving in this direction. This is V. Okay, and let's say that our B is just in the x direction. So like B is some sort of constant times z hat. Or sorry, x hat, not z hat. Let me also label the axes to make this clear. So this is x, y, z, and then v is equal to minus y hat. Let's say it's just magnitude 1. Okay, in that case, right-hand rule, right? V cross b, that's going to push us into the positive z direction. So then FL, in this case, with no electric field present, let me just do this, move this a little bit, v equals minus y hat. So then FL is just going to be the magnitude of v. This is just better if I just do this, minus v y hat. Okay, so as magnitude v, okay. When you do this, you're going to have a v cross b, y cross x would be negative z, and the negatives cancel. And so you're going to have a v times b in the z hat direction. That's going to be the result, the FL. Okay, and like I said, we're going to spend a lot of time with Lorentz Force later, but I wanted to put that in there so you know that it's all about moving charges when it comes to interactions with magnetic fields. Okay, so then the next section is your you might as well call it the Coulomb's law. Coulomb's law of magnetostatics. And that is Biot-Savart. Okay, and this guy is where you have just a steady current, which you can think of as just a line of moving charge. Okay, so steady current, which is like a line of moving charge. That produces a B field, and that B field looks like this. It's mu naught, which is the vacuum permeability, and that one I think is 4 pi times 10 to the negative 7th or something like that. I can't remember the exact value. It's 4 pi times something small like that. It's a defined constant. And so mu naught over 2 pi times the current vector, okay, because current, since it's moving in a certain direction, is a vector, has a magnitude that's like in amps, so the number of coulombs per second or amount of charge per second that's passing through, and then it's going in a certain direction, so that's why it's a vector quantity. You take the cross product of that with r hat, and you divide that by r squared times dl. Okay? And so that's like a very like I said, it looks almost like Coulomb's law, right? You're just taking like a test current and getting a B field by multiplying it in this case like a vector fashion with r hat over r squared. Okay. So like if you have this current I going like this, then what does the B field look like that gets produced by that? Well, let's say that you're trying to figure out what you're feeling here due to this little element, this dl element of I. Okay, well then what you do is you look at r, which is out this way, and then you take the cross product of I with r, and that's going to put you in the, let's see, that would be I, r, so you're going to be in this direction, like downwards, like here. Here, let's draw this. Let's put it like co-located so that it's much easier to see the way the cross product works. So just directly below the element that's the source of the B field that you're feeling, And like I said, the R goes out like this. And so I cross R is going to be into the page. And so you're going to have a current loop that goes around, sorry, not the current loop, a B field loop. That's like a circle going around the current. Starting at that point goes into the page and then out and around and on top of here, this will make it a little bit more clear. So you can see that this passes in front like this. Okay, so it's looping around the current in that direction. Okay, so now we're going to develop another one of Maxwell's laws, like in a very similar way to Gauss's law. And as you might guess, we're going to have to invoke another one of our integral theorems, like in this case, Stokes' theorem. And so, like with Gauss's law, we're going to draw a circular path around a line of current going into the page, okay? Draw a circular path around a line of current going into the page. All right, so that looks like this. So we have the circle looks like this, and it's going in that direction. And then we have, I'm going to draw it as an X because it's traveling away from us into the page, this I vector. Okay? And you want to integrate B along that path. Integrate the B field along that path. Okay, and that looks like this. Integral of a closed loop of B dot dl along that loop is equal to, in this case, we're going to get the closed loop integral. Let's put in the expression for B that we from Biot-Savart. At any point on this loop, the R is pointing directly outwards like this, okay, like perpendicular. And so the cross product will work out where you just get mu naught I on the in the numerator over 2 pi times the radius of the loop of the curve that you're integrating over, dl. And those are all constants. Okay, so you can pull all those out, and you just get this mu naught I over 2 pi RC times the integral over the length of the loop, dl. Okay, and that's gonna pull out the length of the length of the loop, right? And what's the length of the loop but 2 pi RC? Okay, so that's going to cancel out, and you just get mu naught I. Okay. So now let's generalize a little bit here. So we're using a line of current, but like before, how we went from point charges to volume charge densities, right? Let's also introduce the current density. Okay, so the I enclosed by the loop, let's say it's equal to the integral over the surface of the loop times J, which is the current density, J dot dA. So that's the current density. The units of that are like coulombs per meters squared seconds. Okay? And so, now we have this setup where we have the loop integral closed loop integral, of B dot dl is equal to mu naught times the integral of J dot dA. Okay, just from our definition of the current density there. And now we can use Stokes' theorem. So Stokes tells us that that is equal to the integral over that same area of the curl of B dot dA. Okay, and that's true for any loop that we draw. So same sort of argument, and we end up with Ampere's law, which is that the curl of B is equal to mu naught J. So that's Ampere's law for static, constant currents. Nothing's moving, and we'll see how Maxwell dealt with those in just a moment. Those cases, just a moment here. Okay. Okay. All right. So then, if we want to get the Gauss's law of magnetism, it's actually a one-step process here. So to get the magnetic Gauss's law, we actually just take the divergence of the B field. So take the divergence of B as defined by Biot-Savart. So the divergence of B is going to be equal to mu naught over 4 pi. And remember, B is a function of R. So this guy's a function of R. So this divergence, or this gradient operator, is like with respect to R, not R prime. Okay, and so what that allows us to do is we can just take it into the integral. We can flip we don't have to take the divergence of the integral itself. We can move it into the integral because the integral is over the primed coordinates where the source material is, right, or the source current. So then you have the divergence of this vector J of R prime. Remember, that's where the sources are, cross R hat over R squared dV prime. Okay, and then we have this special, this is where we're going to use that special product rule. So product rule, the divergence of J cross R hat over R squared is going to be equal to R hat over R squared dotted with the curl of J of R prime. So this is an important point, okay? So this thing goes to 0, not because J has no curl, but because we're taking the derivative of J, which is only a function of R prime with respect to R. Okay? So like it's almost like saying like I have this current density that's happening here. Okay? If I move from here to here and observe it from a different location, has the current density changed just by me moving? No, it's still just there. So that's why that term goes to 0. And then the next term is minus J dot the curl of R hat over R squared, and that is just equal to 0. You can show this yourself, but this is like, you'd think that the curl of a vector field that's just spreading out evenly in all directions, nothing's going to rotate if you place a paddle wheel in that field, right? So that whole right-hand side actually just goes to 0. And we get this divergence of B is equal to 0. People will often say that this is like your no magnetic monopoles law, okay? And the reason why they use that is because it has the same form as Gauss's law, but there's no, Q over rho over epsilon not on the right-hand side. So you can't make a monopole source of a magnetic field. You need moving charges. Okay. And so let's keep pushing through. So now we're gonna make the leap from static to dynamic. Okay, so here's the thing. Michael Faraday. He's a very interesting chap, okay? So this guy, he was born in 1791. He died in 1867. And this guy, who was like maybe one of the most brilliant experimentalists of all time, he like literally couldn't even do math. Like he could barely do algebra. He didn't know how to do trigonometry. It was Maxwell who translated his work to math. But he made some really important fundamental discoveries. But I always think it's funny to note that this man who laid the foundations and like Faraday's portrait was one of the portraits that would hang in Einstein's office. Like he was very well revered, but he wasn't he was as far from a theoretician as it gets. He was just pure experimentalist, but a brilliant one at that. And so he was messing around with current loops and moving them through magnetic fields. So he moved current loops through magnetic fields, and he found the following. He found that this thing called epsilon, which the name of it is EMF, or electromotive force. I'll talk about that in a second. It's actually not a force, okay? But the way it's defined as the loop integral of E dot dl, which would be along the current loop, okay, is equal to minus the time rate of change of the magnetic flux through the current loop, okay, that through the surface defined by the current loop. So that's equal to, you can write that as dB dt dot dA. Okay, so B dot dA is where you get that flux value. Okay, and so then we use Stokes' theorem. So I should say this is really, okay, so I should clarify. This is the EMF, or electromotive force, is not a force. This is like a misnomer. It's an integral force per charge. To put it simply, you're adding up whatever it is that's driving the current along the loop. So you can write that as the integral of the E field, because it is E fields that drive current. But in real circuits, it's a little bit more complex than that, right? We have like these chemical batteries. The E field is so we kind of wrap all that up in EMF, but you are just integrating the E field along the loop, and that's the way that this was done back in the day. So then we actually are going to replace E dot dl with Stokes' theorem, or using Stokes' theorem, I should say, where we have the curl of E, since it's a closed loop, the curl of E dot dA. Okay, and then that's equal to that surface, or sorry, to the negative dB dt dot dA. And so then we get those two things. We can just pull out Faraday's law. It's true for any loop. So we have the curl of E is equal to minus dB dt, and that is Faraday's law. let's see here, let me get this, write this down a little bit cleaner. Faraday law. Okay. And so now we actually we've seen all four of Maxwell's equations. We're missing one term in Ampere's law, but we're going to fix that in just a second. In order to fix that, we actually have to start talking a little bit more about current. Okay, so it's like that we're continuing that static to dynamic transition here. So let's for a moment talk about charge continuity, which is another way of saying conservation of charge. Okay, so it's almost like a Gauss law statement. It's like the rate of change of charge in a given volume is equal to the total flux of current into the volume, right? Because charge is not going to just appear out of nowhere. So equal to the total flux of charge into the volume. Right? Charged, we're not talking about relativistic cases where mass and charge carrying mass is going to appear out of nowhere. So if that's true, then we can write d by dt of the integral of all the charge in a volume. Okay? So that's like this remember this whole thing is like your Q enclosed in a certain volume. That has to be equal to we're going to put a minus sign here because we're talking, the dA is always the outward normal. So we're actually interested in the flux into the volume. So since dA is always defined as the outward normal, we pick up a minus sign. Okay. And then we can, via the divergence theorem, rewrite that as a volume integral as well. So minus the divergence of J dV. Okay, and then that's true for all volumes. And so we end up with this charge continuity equation, which is the d rho c dt is equal to, or rather even just plus, the divergence of J is equal to 0. That's an important equation. Charge continuity. Okay. So again, very simple argument there. Now, we needed this argument to define this thing called the displacement current. And this is the last bit. This is where we're going to finish up Ampere's law and also just more broadly Maxwell's equations without any mass effects going on. Okay, so the displacement current all right, so Ampere's law has a problem. Okay, and it has to do with this charge continuity equation. So Ampere law has a problem, the way that we've written it so far. Okay, so what we wrote down was the following. So first off, the divergence of the curl of a vector field, which we alluded to before, that has to be 0 always. Okay, that's always true. It's just a fact of math, vector calculus. But if we look at the expression that we had for Ampere's law above, if we take the divergence of the curl of B, right, which is equal to the divergence, mu naught times the divergence of J, using Ampere's law, okay, then we're going to get, via the continuity equation, mu naught times minus d rho c dt, okay, which in general is not equal to 0, right? So charge density might be changing locally, and so we actually have a problem here. We need to add something to this equation to fix the this mathematical inconsistency. This isn't like a matter of like whether or not we're describing the physics correctly. It's like we actually have an equation that just can't be true mathematically by the rules of vector calculus. Okay, so what we do is we say, if we look at Gauss's law, this tells us that the charge density, rho c, I'll just put the subscript on it for now, since I just did the line above, is equal to epsilon naught times the divergence of E, right? That's just rearranging for rho c. So, if we cheekily replace J with J plus epsilon naught dE dt, okay, then the equation behaves properly. Equation behaves. Okay, so what do I mean by that? Now we're replacing J with this, so when we take the divergence of the curl of B, then we get mu naught times the divergence of not J, but of J plus epsilon naught dE dt. Okay. And then the divergence of J would give us a minus rho c, and that rho c would cancel with the other term there, because that's what we get from Gauss's law. Okay, that is equal to 0. So we're doing okay, and then now we can write down a revised Ampere's law, which looks like this: that the curl of B is equal to mu naught J plus mu naught epsilon naught, which, to be clear, is 1 over c squared, times dE dt. So that's actually Ampere's law. And this thing right here is called the displacement current. This was actually Maxwell's big contribution to electrodynamics, and why the set of equations are really named after him, because this was his big insight. The right way of kind of coming up with this is not this kind of cheeky replacement that we did here, but rather looking at, there's two ways. One, you can do, the most elegant way is to do this whole thing from the action principle, all of Maxwell's equations, and I have that in my thesis if you want to look at it, but it's a little bit more high level. And then the standard way is to look at a circuit with like a capacitor. That's the way that Maxwell thought of it, and was able to come up with the idea of the displacement current. But this is like a nice little cheeky kind of way of justifying why we put that there. So there's two other places you can look for that if this was ultimately dissatisfying. Okay, one more thing, and then we'll be done. And unfortunately I don't think it's that short of a thing. Yeah, this lecture is definitely a bit long, on the long end. But okay, so last thing, matter. Okay, so we've developed all four of Maxwell's equations. But we need to talk about what happens when you're in a continuous medium. Okay, so we have Maxwell's equations here for like you're kind of in vacuum and you have some sources of charge here, some charge density, or you have single point charges floating around. It's like, no, what if we're in like some sort of neutral medium? What happens then? Well, when you have an E field acting on a medium, it creates local displacement of charge. So E field, and think of it like on the atomic level, right? Like if you have an atom here, it's largely neutral. You have an electron cloud all around a positively charged nucleus, but the atom itself is neutral, right? If you apply an electric field, what's going to happen is you're going to get a displacement of the electrons downwards, and then the positively charged nucleus is going to move slightly upwards, and that causes what's called a dipole moment. And so you get this net charge, or sorry, net electric field that's produced by this displacement, right? And so the E field acting on a medium creates local displacement of charge, resulting in dipole moment, resulting in a dipole moment. So a vocab word here. Okay, and the dipole moment is just a separation of two charges. And the way you define it, the way it's defined is lowercase p, okay, equal to the integral of r, the separation, of rho c dv. What I want you to have in mind when you think of dipole moment is just two charges. Imagine you just have plus minus E field, okay? And then their separation is d. Okay, in that case, the dipole moment is literally just like, you know, if this is plus q and this is minus q, then the dipole moment is going to be just q times d. Okay, but I'm writing it, when I write down the formula, I'm writing down like for if you had some sort of general continuous charge density. Okay, so now the dipole moment per unit volume, dipole moment per unit volume is called the polarization. Polarization, another vocab word here. And it's denoted with a capital P, and the lowercase dipole moment P is equal to the polarization times dV, okay, for a volume element dV, right? So you if you multiply at a single point, if you multiply the polarization per unit volume times dV, you're going to get the polarization out, okay? Now, this is just a fact. I'm not going to derive this for you, but you can find this, you know, in a bunch of different textbooks online. But the potential due to a dipole, a single dipole, is V of R times 1 over, is equal to 1 over 4 pi epsilon naught times the dipole moment dotted with r hat over r squared. Okay, and that's if here. It's better if I'm just going to make these the capital R's here, so we're careful to keep our old notation, not just placing dipoles at the origin for no reason here, keeping it general. Okay, so we hadn't discussed the potential yet, but the potential is just the gradient of the potential is the electric field. Okay, so they have a very, very similar structure. One is 1 over r, one is 1 over r squared, and this is the potential of due to a single dipole. Okay, far away from the dipole. So you have the E field between these separated charges, but if you go far away, the E field that's produced by this little separation of charge looks like this. Or the potential of the potential due to that separation of charge looks like that. Okay, so then what we want to do is just integrate over the polarization to get the whole potential. So integrate over the polarization to get the whole potential. What does that look like? Well, we get V is equal to 1 over 4 pi epsilon naught, and now we're going to bring in our r's and r primes. So we have our P, capital P of r prime, right? Because we're integrating over those prime intervals. That's where the source is, prime variables, I should say. R minus R prime over the magnitude of R minus R prime cubed, dv prime. Okay, now I'm going to do something fancy. I'm going to say that this, I'm going to replace, and you can, I'll let you check me on this, but you can take my word for it. So you have 1 over 4 pi epsilon naught, and that R over R cubed, that is equal to P R prime. That is equal to the gradient of 1 over the magnitude of R minus R prime. Okay, that's just a vector calculus fact that you can prove to yourself, that that gradient of 1 over the magnitude is equal to that thing on the left. I'm sure the people in the physics who have taken some upper division physics courses have probably already seen this variable substitution, but I'm just doing it here. Okay, and so now we have, we're going to exploit a product rule. So we have this like fact, for example, that if we took the divergence of P over R, okay, which is what this is the gradient with respect to the prime coordinates of 1 over R. That's going to be equal to P dot the gradient of 1 over R, which is that thing that we see here, plus 1 over R times the divergence of P. Okay, so we can solve for the P dot del prime of 1 over R, which is what we see right here, right? And we can turn this into two different terms. Again, this is all just mathematical manipulation, so we'll get to the punchline in just a second. But when we do that, we get the following. We have an integral of del prime applied to P over R minus R prime. Like I said, this is P evaluated at R prime, just to be clear. dv prime minus the integral of 1 over R minus R prime times the divergence of P of R prime dv prime. Okay, and then we're going to use the divergence theorem for that first term, 1 over 4 pi epsilon naught, and we're going to turn that into a closed surface integral, 1 over R minus R prime P, this is the polarization capital P, P prime, P of R prime dot dA prime, and then we're leaving that first term as it is, the minus 1 over R minus R prime, the magnitude of that thing, times the divergence of P of R prime, integrated over a dv prime. Okay, so why in the world am I doing this? This looks so complicated, but there's a method to the madness. So right, so why am I doing this? Well, okay, so I should just, as an aside, say that the potential in general, due to like a point charge Q, right, is just going to be equal to the, that point charge over R. Okay, so if we want to sum up the potential from a bunch of different charges, we integrate over a charge density over R. And so looking at this expression here, we have this 1 over R times some things over a surface integral and over a volume. And so this is kind of like almost like a enthalpy moment in thermodynamics, where if you come up with this definition, your equations become much simpler. So if we define sigma b is equal to the dot product between Pn and the outward normal of the control surface, and rho b as minus the divergence of P, the polarization field, then the equation will look like the potential created by a surface and volume charge density. Okay? So then like your V all of a sudden becomes just 1 over 4 pi epsilon naught, and you just get this surface integral of sigma B over R dA prime plus this volume integral of rho B over R times dV prime. So now you look like just like you're summing up charges to create, you know, from a surface and volume charge density. And so what basically we created these fictitious charge densities that we call the bound charge densities. So they're fictitious, they're fictional, but they produce the same E field or potential as would the corresponding polarization field. Okay, why is this useful? So this allows you to account for the matter producing its own fields. So like electrodynamics seems really complicated because the things that are moved by the electric and magnetic fields also produce electric magnetic fields. So using something like this, we can deal with this continuous mass that seems like infinitely complicated to try to enumerate that feedback mechanism between each individual constituent of a big continuous bit of matter. We can just put this into Gauss's law, these bound charges, and it allows us to take this into account, right? So we can say that the divergence of E is actually equal to rho F plus rho B over epsilon naught. Now rho F is the free charges. So free charge. So free charge is the stuff you control. So this is conventional stuff you control. It's like your test charges. But the bound charge has all that really complex stuff that's going on the inside of the matter, with it becoming polarized at the microscopic level by fields that are incident on the matter, okay? And so what we then do is this, we move the bound charge into Gauss's law, right? Because the volume bound charge rho B was equal to the divergence of P. So now we can move it to the other side of the equation, and you get the divergence of epsilon naught times E plus P is equal to the rho F. Okay, and this right here is the displacement field. This is what we name D, the displacement field. So I told you at the beginning of the lecture we were eventually going to define what D was. And that's how you get it. It's by wrapping up the stuff from the polarization, all the microscopic stuff going inside the matter, into the field that you're solving for. So now you just solve for your displacement field using conventional charges, and you back out the matter effects if you need to. Okay, but generally you're like interested in the displacement field as generally what you're solving for. Okay, and then I know I said that was the last thing, but this is still part of the matter discussion. We need to talk about the dielectric or permittivity tensor. And this is truly the last thing, and it's really quick. So thanks for your patience sticking with me here in this lecture that is turning out to be far too long for a single class. But it's a good thing that I'm recording it. Maybe I'll always just send the students to the video for the first lecture. Probably better just split it into two. Anyways, so then here's the thing. We just went through this whole discussion of polarization. Hopefully it wasn't too confusing. I know I should have talked a bit more about potential before I jumped into that discussion, but hopefully you saw generally the idea is that we're incorporating all those microscopic effects and just kind of smoothing them over and shoving them into the field that we're solving for. Okay, and now we're going to talk about the dielectric or permittivity tensor. So here's something about the polarization. So it turns out that for most substances, which are actually just called linear dielectrics, if you're interested. They're definitely are nonlinear dielectrics. The polarization is always equal to epsilon naught times this tensor chi e dotted with the electric field E. Okay? Tensor, it's a matrix. Okay, think of it that way. It doesn't have any more than 2 dimensions. So this chi e tensor is called the electric susceptibility tensor. Okay, definition. And the reason why it's a tensor is because the medium might be anisotropic. So medium, meaning it might behave differently depending on which direction you're looking at it, or which direction the B field or the E field is pointing that interacts with it, right? So medium may be anisotropic. And this is important for our class here because magnetized plasma is anisotropic. Okay, so then what's going on here? So then the displacement is epsilon times E, but now we're going to replace the P in it with epsilon naught chi E dot E, and now we see that these are both dot products with E, so we can pull out epsilon naught times the identity plus chi E dotted with E, and this thing right here is the dielectric tensor. Dielectric tensor epsilon. Okay, so this is equal to epsilon dotted with our E field E. Dielectric tensor, also known as the permittivity tensor. Okay? So, had to get that down on the page. Like I said, I know this lecture is way longer than it should be. I'm kind of glad I recorded it because to get through it in person would probably take a long time. But please, if you're in my class in person, or actually register for the class, like in person at Oregon State, please reach out with questions. I'm happy to talk about any of these steps in detail. All of the stuff that we cover today is very important. It's all stuff that is going to be a foundation for what we do going forward. I know it was rushed, but this is like me trying to get through kind of upper division E&M in a single lecture. So, but in particular, this permittivity tensor stuff is very important. This is going to be, all we talk about for several lectures is the characterizing the dielectric response of plasma, both magnetized and non-magnetized. Okay, so thank you for watching. I look forward to seeing you all in person. And of course, if you have any questions, like I said, reach out. We can address any bits of confusion. And I hope you have a great remainder of your day. And take care.